Good.
I'm having an anxiety attack
Oh, wow. Why?
because it reminds me of the webinar.
Oh, yeah. Okay, so I'm going to share my screen from the get-go to make sure that we are all set. Looks nice. Okay. Okay. So how many people do you think will be on, Miguel?
I think at least 20.
At least 20, okay.
Yeah.
Yeah, tu peux me passer, bébé. Je vais prendre pendant quelques instants encore, like, there's not people yet. Okay. Oh, okay. C'est quoi ça? Huh? So it's my, oh, God. A question, stupid question, Miguel. If I
Yes.
mute myself, my presentation, if like I put I guess there's no audio for the Loomis video, right? Yeah, because
No,
he's
there's
going to
no
talk.
audio.
Okay,
Yeah.
sure. Okay. And then, like I said, like I'll stop presenting at Jeremy and Anna Maria, and if it's like way past 7, it might be hard. But I think like we also need to be respectful of people's time because Allison has made clear to me that people like why a lot of people were not responding is because it's final and time is really tight for them.
Yeah. Of course.
Okay.
Okay, we got a closing call for 8 a.m. When do we
See, I
expect
have
the
to
closing-
follow this baby
expect the
around.
closing documents? When should we expect the closing documents? When are you going to designate Stockton? We're going to register the
Well,
pool.
eventually,
What's the plan?
Thomas is gonna when he grows older, you're gonna be like, oh, Thomas, you were here.
I know.
beginning.
The only problem also with our house is that there's like we cannot put a baby gate here. So that's why it's really if we were on a one apartment, I was like, oh, there's less. But then there's also like another stair there this way.
It's
And
impressive
so
you guys have 2 floors.
I know for New York City, it's so bomb.
Yeah.
But I'm just saying that like that's why I'm not trying to be difficult when I'm like I cannot leave my children on the floor for 2 hours. It's just impossible. He's 9 months, so he's like pretty agile. He goes up, but like he fell down the other day, and it's like 10 stairs. Like it's like a solid 4. It's like they say 3 or 4 meter up. Like if he falls, like he's dead. So yeah, I'm not trying to be difficult here, but it's the reality of the configuration of our house. Hey,
For a
Julie, you want to
minute,
say?
I thought you. Oh, hey.
Oh, Julian, regarde, montre à Miguel ça.
Wait. Well, I have my mind bigger.
C'est quoi ça, Julian? Tu aimes ça ou pas? La personne est là, un requin. T'aimes ça? Yeah, I just bought his today because we went to a toy shop and he, couldn't leave without having an ocean animal of a sort,
Yeah.
Okay.
You should have bought an octopus.
Yeah. Okay. You okay, sweetie? Good.
Should we post on Instagram right now saying that hey,
Yeah, but the problem with Instagram is like, oh no, oh my God, sorry, Eduardo.
what happened to Eduardo?
Nothing.
Oh no! Oh,
Hi, George.
Hi, how you doing?
Very well. Thank you for joining.
Yeah, this was actually very easy. So
Yeah, so we're waiting for the participant and Allison to join in. We're already live, so Eduardo kindly just reminded me that we're live, which I forgot, and I was speaking with my son and Miguel with a shark stuffed animal. So,
oh.
so yeah. So yeah,
All
I'll
right,
just put myself on mute right now, and I'll wait for other people to join in.
same here.
Okay, speak to you soon.
Hey guys, can you hear me? Hello.
Yes.
Good. How is everybody? Did you send that to Allison? I'm sending it right now, but she said she can find the event. Good. Okay, so you can tell us when we start. We should probably wait until 6 p.m. But let us know when we're live. And thank you to
We're
everyone.
already live, Sandra. Just to make sure that nothing is going wrong. So we're already live, so we should just maybe wait for the other people to join in.
Okay.
Hey guys, on my end, I'm getting a lot of echo.
Can you guys hear me fine?
Yes.
Yes, I can.
Okay. Okay, we can start now. It's 6 p.m. Give me 1 second. Okay. All right. Well, good evening, everybody. Thank you for joining and for tuning in to Papaya's work on calculus. We just wanted to make sure that we help you in your finals. And the reason why we wanted to put this workshop is because I was talking to my good friend, George, who has helped us in our first webinar, Believe in Yourself. I don't know if you were able to watch, but we wanted to be more proactive about people dropping out of engineering degrees. And the reason why we put this workshop is because out of 300,000 in a study found that 300,000 students, a quarter of them failed to get letter C or higher in calculus. And the results are that about half of them graduate with an engineering degree. So that's 1 in 2 who actually get to achieve their dreams. So we wanted to be a little more proactive and help you in your finals. So Papaya believes in inclusion and diversity. So we partner with SWE, and we want to empower women, as I'm one myself. And we talked to Allison, who has been gracefully able to host this event along with George. So they'll take the stage. Just wanted to kind of go over the agenda. We have very exciting topics. We have externship announcements. We have some raffles that we're going to do at the end of the workshop. We also have, we're announcing our new ambassador. And yeah, we just want to work with, all minorities, and we really want to show what we bring to the table. So if we go on the next one. So yeah, looking for externship. So we're going to talk about this later during the break. And, this is a great opportunity to get your feet wet and to really know if you are going to, to school for the right major. We can talk about this later. And then on the next slide, this is very exciting to me. So we met Alexis through Instagram. We used to see that she was a STEM ambassador and an advocate as well for diversity and inclusion. She's a big advocate, so she's going to represent us in the University of Memphis, Tennessee. And she is also very involved with all of the organizations that you see. So yeah, we're going to be putting all minorities together in STEM, which is very exciting to me. Alexis, I didn't know if you wanted to say anything. I think she might have dropped by accident. Oh no, she's here.
Yes, I can. I'm just happy that you're here. Can you all hear me?
And I know you're taking calculus 3, right? Okay. I think she's having mic issues, but yeah. So, well, I'm going to go ahead and introduce Allison, and I'm very excited to work with her. She's the president of SWE. Yeah, so we talked about, while we're putting this together. So yeah, I want to introduce Allison, and I'm very excited that she's going to host this event along with George. I believe in empowering one another, and very impressed with everything she does for the community at the Florida International University.
Thank you, Sandra. For some reason, I can't turn my video on, so I don't know. But thank you for giving me this opportunity today. I'm here on behalf of SWE. My name is Allison Martinez. I am actually a senior majoring in biomedical engineering at Florida International University, and I was actually born and raised in Honduras. So I'm an international student here. And I like to start by saying that they say that behind every successful woman, there is a tribe of other successful women who have their back. And this event is actually one of the perfect examples of what SWE stands for. SWE is proud to be hosting this event especially with a female startup company and with the other collaborators here today. And we as an organization are invested in building an environment to empower women and also underrepresented minorities, and not only in the engineering field, but also in STEM. And this particular event is about helping others. I like to say that we rise by lifting others, and giving students the tools and workshops like this, for example, can help them thrive within the professional field. And you might think that you don't need calculus at all, but this leads me to introduce a very special guest today, which is Mr. George Salazar, an engineer at NASA. And we have a couple of questions from the students at FIU regarding the mission with SpaceX. So George, one of the questions that was popping the most from our FIU students is, how does NASA interact with SpaceX?
Well, hello, everybody. First of all, thanks for having me here. It's a pleasure to support this. I think it's a wonderful organization, to help students. Regarding the question, I think it's a great question. The collaboration with SpaceX is very much, hand in hand in ensuring that the astronauts, in the case of human spaceflight, are safely transported to space station. So the way we work that is that SpaceX is doing a lot of the hands-on design work, but we have NASA engineers working with SpaceX. So SpaceX had, I guess, up to this point, very little experience related to human spaceflight. There's something called human rating of a spacecraft system that's very important for NASA, and there's a lot of steps that you got to go through to get that human rating certification. And of course, Federal Aviation Administration also is involved now because they're a commercial company. Again, SpaceX is now the first commercial company ever to supply a human-rated spacecraft to go to International Space Station. So the collaboration is very close in terms of reviewing designs, attending tests, especially the human in the loop test associated with the astronauts controlling the spacecraft. And then, certainly the most important is the launching of the spacecraft. There's a lot of people involved in that, and even though you see on the television, just maybe a room full of people, but rest assured that, like, for example, Mission Control has somewhere in the vicinity of 50 to 75 people in the background, including where I work in the launch facility, or rather the Mission Control Center. It's called the Commercial Crew Systems, Commercial Crew Engineering Systems room. And so we have a lot of the engineers that work closely with SpaceX to make sure this is a successful flight, and it's just a whole bunch of data. It's just an incredible amount of data to look at, while the mission is going on, making sure that the right calls are made in the event of issues associated with the systems. And there's a lot of systems on SpaceX, and so SpaceX and NASA work very closely together, ensuring that, first of all, it's been certified properly, and then secondly, it flies and meets the objectives of the mission that we're signed up for.
That's awesome. It's really nice to hear from a person who has really experienced that from the inside. It's really different. And moving on to a second question, when it comes more to the calculus principles and engineering principles, what have you heard about the struggles engineer students face when not having the right fundamentals? Like, for example, what are some of the challenges that you have faced personally working with NASA as well, and that you see that some students lack about it?
Oh, well, I have to say that, okay, so here's the thing. I mean, a lot of the students out there are engineering majors, and, for the most part, 99.99% of the classes are all associated with technical skills. Fortunately or unfortunately, it's, I have to say that in the real world, you're actually dealing with more people that that help make a project successful. So you can have a very good technical team, but if nobody can work together because of personalities, egos, and things of that sort, project is considered basically a failure. And so if you look at a lot of past projects, whether it's space exploration or even oil and gas industry, a lot of the failed projects are not associated so much with the technical aspects, but with working with people. And so one of the challenges that I found was actually, the human element, working with humans as far as the projects are concerned. So that's one of the challenges. Second challenge, let's talk about a little bit about the technical aspect, because we're talking here about the calculus and its use in whether it's engineering or different areas of the STEM field. Is the technical, once a student graduates from an undergrad, let's say for example undergraduate in mechanical engineering or electrical engineering like myself, is you just basically have just scratched the surface of the technical challenges that you have up against you. And so once you start working in the area that you get a job, whether it's NASA, whether it's the automotive industry, whether it's aerospace like Boeing or whatever, you're going to have to learn their let's call it the lingo of their technical languages. You're going to have to learn the tools that they use. You're going to have to learn their processes that they use. And a lot of this is not taught in school. And so the challenge is for you to be a very open-minded engineer and basically learn how to learn, if that makes any sense. In other words, you're going to have to learn a lot of things, but you got to know how to learn. And so two things that come into mind that I found very beneficial is, one is that know who to ask, okay? Secondly, know where to look. Those are two critical aspects, even though they sound simplistic, but they're not. They're very important in your career. And so this is something that I had to learn by the seat of my pants. And I'm just sharing with you two simple ideas. And for these two ideas to work, you got to leave your ego behind. If you're a 4.0 GPA, double E or whatever, make sure that you review your ego and make sure that does not impede your learning process, because you can be a 4.0 in electrical engineering, but I guarantee you when you start working, as I found out at NASA, you're at the bottom of the pack. You're at the bottom of learning. And so it's important to understand how to let's call it integrate into a career. And the way that I found is, first of all, and most important, is to have a good mentor. And then that mentor should help you navigate to the areas of know who to ask and know where to look for information, because you don't know everything. And that's something that was a challenge for me at the very beginning, and I had to learn it on the seat of my pants. And I'm sharing it with you within 3 or 5 minutes, but it took me a few years to learn that.
Yeah, that's awesome. It's really nice to hear how you think that it is really important to have a support group, like you mentioned, like a good mentor, people that support you, and like you got to look for answers. I feel like sometimes as an engineering student, you try to solve a problem and you don't stop to think about how are you going to eventually apply this into your field. So thank you for the tips that you have provided, George, for the engineering student. So I think we can move on into our calculus workshop. I guess George gave some tips to unlock your full potential in the engineering school when he mentioned some of the things he had today. But if you have anything else to add, feel free to do so, George.
Yeah, sure. So first of all, we're talking about calculus. So I'm not sure you can see this, but this was my calculus book for calculus 1, 2, and 3. It's called Calculus and Analytic Geometry by George B. Thomas Jr. And it's got duct tape on it because it was falling apart because I kept opening it and closing it and reviewing problems. I have to say that I was very weak in mathematics. I don't want to get into the long story, the history of my high school background, but I was very weak in math, and so in fact I had to go to junior college before I go to university. So I had to take intermediate algebra and college algebra and something called elementary functions before I could even take calculus. But one thing that I struggled with initially when I moved over to engineering, because I first started out in technology, was that I was first trying to compete with students that were very good in mathematics. And so, and when the grades would come in for testing, I would find myself, kind of at the lower bottom of the grades, and it was very disappointing. But later, I just decided, you know what, I'm not going to compete with anybody. I'm going to do the best that I can, and that, it is what it is, okay. And so, but I said, you know what, if I'm going to do the best I can, I'm going to do everything in my power to get the best grade that I can. And so what I did, as far as tips are concerned, it wasn't just calculus and differential equations and some of the higher mathematics associated with electromagnetics. Was that okay? These students, obviously are very sharp and much sharper than I am. I got to work twice or three times as hard. So I just knew that I had to work harder. The same thing as for those of you who do running. If if you're trying to run a under 6 minute mile or a under 5 minute mile, you're not going to do it by just running a couple of times out of the week, and maybe a couple of miles out of the week. You're going to have to keep practicing, and so that's what I did. Every time I had a chance, I was studying problems. I would take problems. Solutions to problems that were given after we turned in our homework and found out all the mistakes that I made, is I would over and over and over again until it settled in. First of all, what did I do wrong? And then secondly, how can I approach the problem differently? And those were the things that come to mind right now as far as studying tips, whether it's calculus, whether it's mechanics, whether it's physics, whether it's electrical engineering, chemical engineering, or whatever, is that there's going to be some topics that just are foreign to you, and it's just very hard to comprehend. And one of the reasons sometimes it's hard to comprehend, unfortunately, is that you may have a professor that's very academic and teaches theoretical stuff that wants you to become a research engineer. A lot of us don't want to become research engineers. I didn't want to become a research engineer. I wanted to take engineering and apply it to developing systems. So, but you got to deal with that. So, unless you have a great professor that worked in the industry and said, I had a Cal 2, I'm talking about calculus. I had a calculus 2 professor. A lot of students were dropping out of calculus 2. They were not making it. Even I have to tell you, I had my brother-in-law scored 1,500 on an SAT. All right, 1,500 is not too shabby. He could not pass calculus 2. All right. And so there were some other ones that just couldn't pass calculus 2. Well, luckily I had an organization that shared with me which professors to take for calculus 2, and I took a professor that was a practical engineering professor. He had worked at Applied Physics Lab out in Boston. He worked at MIT in research labs. And so when he taught calculus 2, he taught it from a practical standpoint. And so the practical standpoint was he gave us problems that were practical and not what he considered mind exercisers. I'm not going to say that you're going to get that kind of professor. I was very fortunate to have a Cal 2 professor like that. Cal 3 was just the opposite, but be that as it may, I strolled and made it through there. But it's important to understand, where your limitations are, and sign up to the fact that you're just going to have to work harder. And so there's a slogan or a motto that I came across many years ago that's very true. It's 10 two-syllable words that can be very powerful, and it's just like it goes like this: if it is to be, it is up to me, right? So if you want to graduate, it's going to be up to you, all right? And you're going to have to find that avenue to help you graduate, whether it's studying, 3 or 4 times as hard as anybody else, hiring tutors like Papaya, to help you. It's a matter of how much you want it, how much is burning in your heart to make that happen.
Wow, that's great advice, George. We appreciate it. So I think now it's a good time to do like a little segue to the to the workshop. I know that George, you can introduce our first tutor. His name is Jeremy. So, and you guys on, especially the people on the YouTube live, you can stick around until the end because like we would like you to comment, and there will be a raffle by the end, so you can get free tutoring and a lot of papaya swag. So we can go on with Jeremy. So I will drop my presentation and Jeremy can start presenting his presentation on limits. So that's the first topic for today.
Yes, thank you, Gabriel.
Welcome all the students that just came in. I can see that there's a few of them that just joined the chat. So thank you for joining in. We're starting the workshop strong. So there you go.
So, can you see my presentation? Sorry.
Yes, we can.
Yes, thank you. So, hi, my name is Jeremy. I am 23 years old, and I am currently a senior at bioengineering at UTech. I love to read horror novels and watch movies. So, today I'm going to do a quick overview about limits. First, let's talk about the concept of limits itself. So, now, imagine that you are chilling at your sofa watching Netflix, and suddenly you get very, very hungry. Okay? Then you remember that there is a hamburger at your kitchen. So you stand up and you begin walking towards that hamburger. Okay? In that moment, your mother appears and she sees you going for that hamburger. And in that exact moment, she thinks that the limit of you when you are moving towards your kitchen is that hamburger. Okay? So that is the simple concept of limits. You being the function and the hamburger being the number that you are approaching. Okay? It doesn't really matter if you actually catch your hamburger. Okay? What matters is that you are approaching and you are very, very close to that hamburger, which is the number. Okay? Now, when we want to calculate the limit, you first need to start with a simple step, direct substitution. You plug in the number of the limit, and then you can get three answers from there. Okay. First, you can get a real simple number. When that happens, you basically finish the whole problem. Okay, in your exam. Normally, that doesn't happen, sadly. So the other possibility is that you get a division where the denominator is 0. That if you graph that function, it will give you an asymptote. Okay? And the last possibility, and the most common one, is the indeterminate form, when you have a division where is 0 under 0. You cannot have this answer because it basically doesn't exist. Okay? So when this happens, what you want to do is you want to rewrite the limit through factoring, conjugation, or trigonometry identity. After that, normally you can plug in the limit number again, and you will get a real number. Okay. Sometimes when that doesn't happen, when you simply don't get the answer, you can always get it through the graph of the function. Okay. So you can graph the function and evaluate each number until you obtain the limit number. Okay. So now I'm going to talk about limit laws. Limit laws are really, really simple. Okay, let's start with the first one, the sum. When you have the limit of the sum of two functions, you can separate that limit. Okay, let's see here. When you have the limit of 4x plus 5x, you can separate that limit with limit of 4x plus limit of 5x. And the answer will be the same. It's again, with difference is the same. You know, when you have the limit of the difference of two separate functions, you can separate that limit. okay? Here you can separate this function to the limit of 9x minus the limit of x divided by 4, and you will have the normal answer. When you have a constant, what you can do is you extract that constant from the limit, okay? What you can do is, it doesn't matter what type of constant it is. It could be 50, it could be 2.4, or it could be like a square root of -1. It doesn't really matter what type of constant it is, okay? What matters is that you can extract that constant from your limit, and you can proceed to change the limit by the limit number, and you get your answer, okay? Now let's go for the next. So the product. When you have the product of two separate functions, you can separate that limit, the same as the sum. You know, when you have the limit of sine of x multiplied by the cosine of x, you will get the limit of sine of x multiplied by the limit of cosine of x, and you will have the answer. It's the same with coaching, okay? Like here you can see that there is two different functions here in this division, okay? So what you can do is just say that each of the parts of the division has a limit, and then you can swap the variable by the limit number, and you will get your answer. Now with power and with the root, it's the same, okay? You get that root, or you get that power, and you extract it from the limit, right? And you swap the number, or the limit number, inside of the root or inside the power, and then you take into consideration that power. Now let's talk a little bit about a really simple problem, okay? Here we have the limit of u going towards 2 of 4u plus 1 square root all minus 3 divided by 2 by u minus 2, okay? So first, as always, you need to plug the limit number, okay? So you swap the number, and as you can see, we get 0 under 0. So this is the indeterminate form that we talked about before. This is what you don't want to have, okay? So here, as you can see, there is a square root. So when you have a square root, you usually conjugate the whole equation, okay? So for this, we need to remember this property, okay? So you have this function where there is the square root, and you multiply it by a similar function. So you can, this first part of the function, you can power it by 2. So the square root is gone, okay? So we do that, we multiply this part, and we multiply the denominator, and we will have this. After this, we operate the plus 1 minus 9, and we will have this 4u minus 8, okay? Now, as you can see, we almost have the full answer. Now, you factorize the 4, so you can have 4 multiplied by u minus 2, and what you do is you just eliminate the u minus 2 in the upper part and in the lower part of the division, okay? And you will have the answer of the whole problem, okay? You now, after you conjugate the equation, you swap again the number, and you operate it, being the final answer 4 divided by 6, okay? Now, let's go with a different problem, okay? What is the answer of the limit of x going towards infinity positive of 3x minus 1, all of that multiplied by 4x minus 2, divided by x plus 8, multiplied by x minus 1. Okay, so first, when you have that infinity, you normally cannot plug in the number since it is infinity. Okay, so first you start by simplifying the equation. You just multiply these two functions here and these two functions here. You multiply them, and then what you need to do, this is a little trick, all right? What you need to do is that you need to divide the function with the x that has the biggest exponential. All right? In this case, is x powered by 2. Okay? So you divide the whole function by that exponent. So now that we have this function, now we divided everything by x powered by 2, and we will have the limit of x going to infinity positive of 12 minus 10 divided by x plus 2 divided by x powered by 2. And in the denominator, we will have 1 plus 9 divided by x minus 8 divided by x powered by 2. And now, remember, when x is going towards positive infinity, then when you have a number divided by x or positive infinity, it will go towards 0. The limit of that division will be basically 0. Okay? So now you swap the whole x, all of the x by infinity, and you divide. All right? You will have now 12 minus 0 plus 0, and in the denominator you will have 1 plus 0 minus 0. That the final answer will be 12. Okay? And now I am going to end and give you the word with Ana Maria. All right?
Hi guys. So I'm going to present right now. Yeah. Okay, can everyone see? Yeah, great. Okay, hi, I'm Ana Maria Perez. I'm majoring in mechatronics engineering at UTEC University in Lima, Peru. One of my hobbies is painting, and I also played varsity basketball at school, which actually allowed me to participate in a South American competition representing Peru, which was really cool. And now I'm going to kind of explain a little bit about derivatives. Okay, so we're going to go through our theory, a little bit of strategy about how solving problems, and then a big problem that I encountered in one of my practice exams in college. Okay, so first theory. So I'm a pretty visual person, so I'm always trying to find graphs and things to kind of understand math. So I also found this kind of representation of how derivatives work, and I'd like for all of you to see it. So as you can see, derivatives, basically what they do is they explain how the slope of the tangent in a function is changing. So as you can see, whenever the slope is the tangent, it's kind of vertical, or horizontal, you can see that in the function of the derivative, that is this one, it's 0. And it happens in a lot of times in every function, in almost every function. So let's go back to the slides. So as I said, here you can see how in V, in both times, when the tangent is horizontal, the derivative is 0, explaining that the derivative describes the changes in the slope of the tangent at every moment in the function. So let's go throughout the strategy. Okay, so these are basic properties and rules that kind of describe the relationships inside the functions and how to solve these relationships accordingly. We also have some common functions such as trigonometric functions, exponential, logarithmic functions, and how to solve them. Okay, so we're gonna go through this easy problem. And you'll see throughout solving different derivatives that the most interesting kind of large problems are just common functions are related throughout the chain rule, throughout the product rule, or others. So a great hack is just trying to find these common functions and try to solve them kind of individually. So that's what we're going to do right now. Okay, as we can see, kind of the main element of this function is the sign. Therefore, it's a kind of trigonometric function. We can also see that, and the trigonometric function is solved by this derivative. We can also see that inside the sign there's a natural logarithmic, which is a logarithmic function that is solved this way. So you can see that there are like just common functions that we always encounter, but they are related amongst each other in this kind of bigger function. We can also see that this logarithmic function is added to an exponential function that is also within the sign, and it is solved this way. And they are all related throughout the chain rule. The chain rule basically says that there's a function within a function, which is basically what we're seeing right here. So let's see how to solve it. Okay, so here we have our function. And the chain rule basically says that when there's a function within the function, you derivate the kind of bigger function and outer function and keep whatever is inside the same, and you multiply it by the derivative of whatever is inside. So we have like these two big elements, or two principal elements. So let's kind of identify them separately and then solve it. Okay, so we have the outer function, which in our case will be h, and it's as the sign of gx, when gx would be our inner function. So here we have gx, our inner function, and here it's the logarithmic of 4x plus e to the power of negative 2x. So let's first solve this, the outer function. As you can see from our common functions, the derivative of a sine is just the cosine. And since everything inside needs to remain the same, we just keep gx the same. Okay, so now we just replace gx for its value, and here we have already our first element of the derivative. Okay, the next step would be derivating whatever it's inside the general function. So let's derivate it. Okay, so as you can see, this function is just two little functions added together. So one of our rules or properties of derivatives is that when you derivate two functions or more that are added or subtracted together, it's the same as derivating each one individually. So that's what we're going to do. So first, we're going to derivate the natural logarithmic. So by our list of common functions of natural logarithmic, we can see that the derivative of a natural logarithmic is the derivative of whatever is inside as the numerator, and you just keep it the same as the denominator. So now we go to our second little function. So plus the derivative of e to the power of negative 2x. Okay, so we can see that this is how to solve, an exponential function. So we kind of just do that. We put the derivative of the exponent here, and we just keep everything the same. That's how you solve that common function. So just simplifying everything, getting rid of the force and multiplying plus by negative, you have negative, and you already have these two elements of our derivative. So the only thing we're left to do is just multiply them, and here we have our solution. So as you can see, it's just kind of trying to find these little common functions, see how they are related by the chain rule, by the product rule, by the quotient rule. There are different rules and properties, and just kind of go through there. And as you practice more and more, you're just gonna spot these rules and relationships immediately, and you're going to be able to just solve them. Okay, so we're gonna go and try a kind of harder exercise. This one I had in one of my exams, one of my practice exams. Actually, the principal, bigger exams are way longer and yeah, way more exhausting to solve. Okay, so I try to find a problem that has to do about changes in time, which is one of the main uses of derivatives. So here we have a system, a piston cylinder system, which consists, which has a crank, and the crank is moving the piston left and right. So, and it's moving with an angular velocity of 0.85 radians per second, and the piston has a 4 centimeter radius. So what the problem is asking from us is to find the rate of volume change of the cylinder when alpha, which is the angular position, is pi over 2. Okay, so let's see our considerations and basically how we solve this kind of problem. Okay, so we have to see what's changing inside the volume of the piston, of the cylinder. As you can see, the area of the piston actually stays constant. So the only thing that actually changes in time in the cylinder is this h, which is the length. Here we also have the volume of a regular cylinder, where here the area would be maintaining constant throughout time. We can also see that h is kind of related. The change in time of h is related to the change in time of x. So that's going to help us a lot. But we also need to get in mind that when x decreases, h increases. So they're actually related, but when h is positive, x is negative, basically. So another interesting property is the angular velocity is the derivative of the angular position. So let's go ahead and solve our problem. Okay, so here we have this is what they are asking us, the change of volume in time. And since this basically is a constant, it's as we said, the area keeps constant in time. It's not derivated. And the only thing that we are derivating, or the only thing that we actually need to find, is this value. Okay, so the only data that they actually gave us that has anything to do with changes in time is the angular velocity. So we need to find an equation or a function that kind of relates this x with the angular velocity. So that's when the law of cosines comes into consideration. So just applying this law of cosines, because it has the x and the angle, applying this law of cosines to our own triangle, we have this equation. Now, in this equation, we can see x and we can see alpha, and we have all of the values that we actually need. But what we need to find is this, which is the derivative of x. So let's just go ahead and derivate the whole equation. Okay. So one of the properties that we saw before is that when you derivate functions that are added or subtracted, you need to kind of derivate them individually. So that's what we're going to do with each one of these. Okay, so now let's go ahead and see how these get derivated. So let's have these properties in mind. When you derivate a constant, the result is 0. Therefore, these two are 0. When you derivate this kind of function, you have to kind of put the exponent down and subtract 1 from the exponent. So we're basically left with this. One of the other properties is that when you are derivating a function that is being multiplied by a coefficient that is constant, it can go out of the derivation. So we are left with this. Let's see something that we can maybe subtract from the equation to make it easier. Let's see, we can erase these 2's. And yeah, well, the 0. So let's go ahead and keep solving it. So we are left with this equation. This is already derivated, but we need to derivate this part. Okay, so the product rule, which is basically how these two kind of little functions are related, says that when you derivate two functions that are being multiplied, the result is the derivation of the first one by the second one plus the first one by the derivation of the second one. So that's what we're going to do. As we can see, the derivation of the first one, that is x, would be 1, which is here. And the second one just stays the same, which is cosine of alpha. Since the value that we derivated is x, we here need to put the derivative of x over it in time. So it would be plus the first kind of function, it stays the same, and the derivative of the second one. In this case, the derivative of cosine, is the negative sine of alpha. Since the function that we derivated is this one, we have to put the derivative of alpha in time. So there we have it. The only thing left to do, since we already got the value that we needed, which is the derivative of x in time, is to factorize it. Okay, so factorizing it, putting everything to the left, to the right, and kind of make it so we can understand, we end up with this function. Okay, so we already have this that we needed, and we have to take in mind that this was already given to us by the problem, and also alpha. Okay, so alpha being pi over 2, and the angular velocity that is the same as the derivation of the angular position is 0.8 pi radians per second. We can replace these values in our function. So the sine of pi over 2 is 1. So this just gives the same, so 1 goes here. And also the cosine of pi over 2 is 0. So this whole value here, by. Okay, so the great thing about this problem is that it puts us in a position that we can actually eliminate these two x. 1 here and 1 here. And so this negative goes and affects the whole kind of numbers and makes 5.58 a negative. So one of the things that you have to keep in mind, it's happened to me a lot, that in exams you don't really take in mind of putting your calculator in radians, configuration in radians. So it's like you have everything done, but then you put your numbers in your calculator and it's not in radians and the number just isn't right. So just keep that in mind. So, okay, so just multiplying our two numbers that we have left, we have that the change of x in time is negative 14.02 centimeters per second. Okay, so, but they are not asking for the change of x in time, they're asking for the change of volume in time. So we already have all the kind of values, so we'll just have to replace them. So we are kept with this function. So further analyzing it and getting those numbers in the calculator, we have that the change of the volume in time equals 704.72 cubic centimeters per second. You also have to take in mind that you have to put the units. Some professors let it slide and don't take points away from you, but as an engineering, it's a good practice to kind of have those units there, because as you get more into college, you'll see that you have to work with a lot of different types of unities and types of quantities, and having your units there helps a lot. Okay, so now responding to the question that was presented, what is the rate of volume change of the cylinder when alpha is pi over 2? So the rate of volume change is 704.72 cubic centimeters per second. Yeah, that's everything. We already solved the kind of big problem. And as you can see, the part of derivating, it's not actually the kind of hardest or more interesting part, but it's actually finding the function or equation that you need to derivate. So here practice comes a long way. This way you can see different systems and different kinds of problems, and actually and practice how to connect all the previous knowledge about geometry or maybe a little bit of physics into math problems. So that's everything from me. Thank you. And here now we go to one of my one of my friends, and he'll explain another subject.
Okay, before we before we go any further, I just want to make a couple of comments. Jeremy and Ama Maria, great presentation, a lot of good information. So I want to ask you both because there's something that just came across with your explaining this that I'm reminded of some of my former college students that struggled with. If you're not strong in algebra, it can be very challenging to do calculus. Is that a correct statement?
Not really, like the simple kind of problems, but the one that comes with context, and they a lot of them require a lot of previous knowledge of other subjects from you. So one of the things I like to do is it's hard for me to kind of study or practice on my own, but in college I had this, they have the system that there is kind of older student that likes to solve hard problems with context in kind of classes. So I'd always go, and even if I had another homework or something else to go through, I'd always go so I could see how he uses other kind of knowledge of physics or something else, and he applies it into math problems. So that's what one of the tips I had. Yeah.
Yeah, I recall that in my calculus 1 and 3, the professor would say, I want the answer in this form. And so you had to do a lot of manipulation, divide or multiply both sides. And so if you don't understand what you do to one side of the equal sign, you have to do it to the right side. You can quickly not have the right answer.
Yeah.
And so,
Yeah.
just some, these are just very fundamental things that can get you tripped up very easily.
Yeah.
Understanding trigonometric identities, okay? Cosine of 0, 1. It's a simplicity game, but if you don't know your trigonometry very well, you can go off into the weeds, trying to answer those kind of questions. So it was just an observation that I made. Again, it goes back to understanding your fundamentals before you start moving on.
Yeah,
The second thing. Yeah, the second thing is, I'm the different, the derivatives and all that in electronics, we use that quite a bit. And interesting enough, the equal sign, sometimes people don't understand the equal sign says it's a balanced equation. Left side equals the right side, so it's balanced. But many times in engineering, you're trying to make something bigger than, making it imbalanced. Like, for example, I can give you an example of a resistor. We do the calculations. We come up with equals 50 ohms, but we want it bigger than 50 ohms. So we have to make the equation say greater than 50 ohms. And so you do the calculations. And that's something else that you have to be aware of, that equal sign is only when you're trying to balance, both sides equally, but many times you want it to go this way. But very good presentation. I appreciated that.
Thank you.
Thank you, George. Thank you.
So now it's time for Jose Martin to present the integrals part. Thank you, guys.
Okay, perfect. So I'm gonna put my screen right now. Okay. Second. There. Okay, so hello guys, my name is Jose Martin. My major is in industrial engineering. I come from the same university as Ana Maria and Jeremy. I'm from UTEC. Obviously, I'm Peruvian too. Okay, so we're going to learn integrals today with me. So to put it simply, we can first assume that integrals are just the opposite of the derivation. So here I have there's a set of functions that I'm showing to you. They all have one thing in common. They have one of its components is x squared, but they are different because they have different constants in addition to them. But as you may know, if we derivate each of these functions, we will get the same result, which is 2 times x. So based on this concept, we can understand that one function, when integrated, can have many different results. So this is what we call an indefinite integral, which means that the integral of a function can be any of the possible antiderivatives of this function plus a real constant that should not have anything to do with the variable itself. So it has to be a real constant that doesn't have the letter x involved in it. So as long as the derivation of this antiderivative equals to the function that we've been working on in the first place. So this is the first idea that we have of integrals. But you might ask yourselves, so okay, integration is the opposite of derivation, but why do I need to do this? What does this mean? What is the use for this? So let me propose you guys a question. So let's say that we have this function. This is a very simple function. It's x squared, and we're going to plot it from 0 to 2. And I'm going to ask you the question, what is the area below this curve? So I want to find out what is the area that is below this line. So this whole region, I want to know, I want to know what is the area of this whole region. So how can I do that if I just know basic geometric concepts? I know how to calculate the area of a triangle, of a rectangle, but I don't really know how to do this with this curve, because this is not really a circle, isn't it, right? So since I don't know, the same question was pondered many years ago by some very famous mathematicians, and one of them, called Riemann, proposed that we should divide the area below the curve in rectangles. And he said, if we start using more and more rectangles, the shape, because as you can see, if we use just 1, 3, or 5 rectangles, we don't really have the shape that they take isn't really the same as the area that we're trying to calculate, right? But if we start using more and more rectangles up to an infinitesimal point, we will get very close, or we will reach the limit in which we can safely calculate or assume that the area calculated by adding the areas of these very thin rectangles will become the area that we're trying to calculate, right? So later, Newton and Leibniz developed this concept, and they came up with this expression that is known as the Newton-Leibniz axiom, and which is the basis for the definite integrals. So it says that as long as we know the start and end point of this function, we can calculate its area by integrating from point A to point B the function in x. This means that we're working the integral in x just by evaluating the antiderivative of this function by the upper bound and then subtracted by the lower bound. So what does this mean? I'm going to explain you very quickly what does this mean. This is the symbol for integration, and based on what we just saw on the model proposed by Riemann, I just want you guys to know that this is just a big S, at an elongated S, because integration is nothing more than an infinite sum. So we're just adding things up until we get to a result. Okay. So if we start understanding integral as just a big sum, I think that's going to make things a lot easier. So going back to the question that I initially proposed, is what is the area below this curve? So we're going to use the two concepts that we just learned to do this. So in order to calculate the area, we know that the function that we're going to be working on is x squared. So using the first concept, which is the concept of integration being the opposite of derivation, we're going to calculate the antiderivative for this function. So what we're going to do is apply this small rule with this very easy and basic rule, which says that whatever we have as an exponent for x, we just have to add 1 Remember that in derivation we had to subtract 1. Okay, so in integration we have to add 1 and then divide the whole expression by the new exponent that we got. So since we're working with a 2 here, we're going to apply this and we're going to add 1, so this becomes an x cubed, and then we're going to divide this by 3. So we have an x cubed over 3 plus the real constant that it can be any number that we want as long as it doesn't have the x involved in it. Okay, so the antiderivative is just that expression without the constant. Okay, so x cubed over 3. So in order to calculate the area, and since we already know the antiderivative for this function, we just use the Newton-Leibniz axiom, and we evaluate the antiderivative on the upper bound and then subtract it by the lower bound. So see, this is a very simple example. And we just plug the numbers in on this function, and we get 2 cubed over 3 subtracted by 0 cubed over 3. So the result that we're going to get is 2.666 to infinity. But this is like the most basic use for integration. And actually, this question, like how to find the area below the curve, is the one that sparked this whole concept, and we can delve so much deeper into this. So we're gonna jump right now into a slightly more difficult problem. So this is actually a problem used in my university for Calc 1. This is a test problem for the summer semester, if I remember well. So what does it say? It says that in a club, a ramp will be built with the following dimensions. Okay, so they already give us this graph. And it says the lateral space available must be used for advertising. So what is the maximum possible profit if advertisement companies pay $105 per square meter available? So we know that this curve is described by this function, which is already provided to us. There is a smaller ramp here that we're not going to be able to use for advertisement. So if we use the concept of integrals as the calculation of an area below the curve, we can easily do this problem. So first, we have to put our problem in context. Okay, so whatever they ask us to do, we have to identify which mathematical principle we're going to use to solve this. Okay, so since they are talking about areas and we have curves, okay, curves below the area means we're going to integrate. So since we're only using the area on the side, we're going to calculate the large area, which is the area highlighted in yellow, and then we're going to subtract it by the area painted in green, which is the small area, described by this straight line. So the revenue, which is the what we're trying to find out, because we want to make a profit out of this wall, is going to be $105 times the area that we're going to calculate. So this area is going to be equal to the large area subtracted by the small area. And as we already know, because we already know integrals, the large area is going to be the integral from 0 to 4 of this function, which is 1/2 plus 7 over 4 times x squared plus 2. And the small area is going to be the integration from 0 to 1 of this line, which we don't know the equation for yet. So the first thing that we have to do is to calculate the equation of this straight line, and this is very easy to do. We since we already have some points plotted out for us, we just use the 2-point strategy. So we pick any two points belonging to this line, and that's enough information to calculate the equation of this line. So the first point is going to be 0 on x and 1.5 on y, and the second point is going to be 1 on x and 0.5 on y. So we just plug this on the on this equation, which is y equals the slope times x plus the independent term, and we find out that 1.5 equals the slope multiplied by 0 plus the independent term. Then using the first equation, we find out that the independent term is going to be 1.5. And then using the second point, which is 1.0.5, we find out that 0.5 equals the slope multiplied by 1 plus the independent term. Since we already know it, we just put it right there, which is 1.5, and we find out that the slope is actually -1. And we can clearly see that it is a negative slope because the line is going downwards. So therefore, the equation for our line is going to be -x plus 1.5. Okay. Since we already have a function of the line, we're now able to calculate the small area. So we're just going to solve the integral. We go from 0 to 1, and this is the function that we're gonna integrate. So remember the rule that I just showed you. X is X is already has a potency of 1. So what we must do is just add 1 to the one that is invisible here, and we get a 2. So we get an x squared over 2 because we also have to divide it by the exponent. So we have a -x squared over 2, and then we add 1.5 times x. Any constant that we integrate, we can assume it's multiplied by the variable, which is x, to the potency of 0, because x to the 0 is 1. So if we have x to the 0, we just add 1 and we get x to the 1, which is just x. And we evaluate this function in both the upper bound, which is 1, and the lower bound, which is 0. How do we do this? We just plug this value in, and we get -1 squared over 2 plus 1.5. And then we subtract it by the same expression, but evaluated in 0. So it's -0 squared over 2 plus 1.5 times 0. So this whole expression, we can just get rid of it because it's just 0. And we find out that the small area is actually just 1 square meter. See, so super easy. So since we have the small area, we're going to calculate now the large area. So in order to do this, we're going to use a neat little trick. This is actually a very cool technique, which is called a trigonometric substitution. So I'm going to go into it right now. So this is the expression that we're going to integrate now. It's we have to go from 0 to 4 for the function that was given to us, which is 1 over 2 plus 7 over 4 times x squared plus 2. So the first term is like very easy to integrate. It's just x over 2 because this is a constant and we just multiply by x. But the second one goes to in order to do the second one, we have to use this technique which we call trigonometric substitution. We cannot use the basic technique that I taught you a few slides ago because this is a division and the x is on the denominator, and on top of that it is squared. So there's not really any way to put this back in or back on top of the division without having to do something with this too. So what I want you to tell you guys here is that the important part is not that you really have to memorize the whole procedure for a trigonometric substitution. What is important is that you have to begin to understand and identify the structures or the patterns that are going to be shown to you, and that are going to straight away tell you which integration technique is going to be the best one for every situation. So whenever I see a division, when I have the variable squared, I already know that I have to apply this technique, which is trigonometric substitution. So how are you going to do this? Okay, so first we're gonna draw a right triangle. And okay, on the hypotenuse, we're gonna put the denominator square rooted. Okay, so we have the square root of 4 times x squared plus 2. And on each cathет, I'm going to put each term square rooted. So on one side, I'm going to put, I don't think it's very clear here, but I'm putting 2 times x on the right, on the cathет opposite to this angle. And on the adjacent cathет, I'm going to put the square root of 2. So actually, I just separated this expression here, and I I called it I because I'm just going to work on this one for now. So we're going to give it the proper shape. So we took the 7 away. So we have 7 times the integral of 1 over 4 times x squared plus 2 in respect to x. And we're going to do that trigonometric substitution. So theta is going to be the arc or the angle whose tangent is going to equal 2 times x over the square root of 2. So the tangent of theta, which is the variable that we're going to be replacing x for, is going to be 2 times x over the square root of 2. So then we just multiply the whole thing by the square root of 2, and we get that 2 times x equals to the square root of 2 multiplied by the tangent of theta. And then we can safely derivate this in order to also replace the differential term. And we get that 2 times the derivative of x is going to be the square root of 2 multiplied by the square secant of theta multiplied by the derivative of theta. So we replace this term 2 times x here because this is 4 times x squared equals to 2 times x squared, and we're just gonna put it right here. And we're going to also replace the derivative of x as the square root of 2 divided by 2 multiplied by the square secant of theta by the derivative of theta. So that's what we have right here. So this is very important. We have to remember our trigonometric identities. We have to know that 2 times the tangent squared of theta plus 1 equals to the squared secant. So actually, this whole thing we can factorize the 2 in this denominator, and we can cancel it out with a square secant that we have right here. So we end up with just 7 times the integral of the square root of 2 divided by 4 of the differential of theta, which equals to the 7 times the 7 times the square root of 2 divided by 4 by the integral of the differential of theta. And the integral of the differential of any variable, it's just going to be the variable because that's the antiderivative. So in the end, this expression is going to be 7 times the square root of 2 divided by 4 multiplied by theta. But we know that theta is already the arctangent of 2 times x divided by square root of 2. And that's how we plug it in right here. So we have the whole expression. Yes, the same numbers. Well, but they're expressed in a different way here. Sorry. Multiplied by the arctangent of the square root of square root of 2 multiplied by x, and then we just do the same evaluation. We evaluate this by the upper bound, and we subtract it by the lower one, which is 0. So in order to calculate the revenue, we end up calculating the second area, the large area. So we just plug it in this whole function. We plug it in the 4, and then we plug it in the 0, and this is what we get. This is the whole expression that we get. Actually, again, the part that is applied to 0 just cancels out because the arc whose tangent equals to 0, because the square root of 2 multiplied by 0 is 0, is actually just 0 because it's a very, very small angle. Like because the larger the angle, you have a bigger tangent. So if your tangent is 0, then that means your angle is also 0. Okay, so we just get rid of this whole thing, and we can actually just calculate this, and we end up with approximately 3.45 square meters. So the total area is going to be 3.45 subtracted by the small area, which is just 1. And then we just multiply the values, which are going to be 105 times the area, and we get the final result, or the maximum available profit. Okay, so as you can see, actually the algebraic part wasn't really that hard, as long as you remember your trigonometric identities. So yeah, okay, that's pretty much it. So I don't know if you guys have any questions.
No, that was great, Jose. Thank you so much.
Mhm.
Now, I think we're going to segue directly to Gerardo because we're a little bit behind and we want to be mindful of everyone's time. So, Gerardo is going to do the logistic curve. And Jose, can you please stop presenting so
Sure,
Gerardo
sure.
can follow? Thank you, guys.
Okay, done.
Okay. Well, hello everybody. My name is Gerardo. I'm going to start presenting right now. Okay. So there it is, right? Okay. First of all, I wanted to talk about myself for a little bit. I'm 42 years old. I've been married for 7 years now. I have a couple of twins who are going to be 3 on January, and who are a little bit stressed from because of the lockdown, right? Anyway, their behavior is kind of a misbehavior, but well, that's going to pass, right? Right now, I'm going to talk to you about an application of a derivative of a function, which is the logistic curve. Okay. Okay, that's the plan. And I want you to take a look at this chart here. Okay, I took this chart from the John Hopkins University um, data. Okay, this is the website. I I I got this chart. They give us the number of cases of coronavirus in different places around the world, right? Different countries. Um, for example, we have an orange curve right here, right? The orange curve uh, tells us about the number of cases of coronavirus in India, right? See how this is behaving. See how this curve is behaving. Around June, probably, the number of cases began to grow very fast, right? Began to grow very fast until one point, maybe around September. Of course, the number of cases continued to grow, but not as fast as before, right? So the speed at which the number of cases grew decayed a little bit. Anyway, right now this curve seems to be stabilizing, kind of, right? Okay, let's take a look at another curve. For example, this curve right here, which is from Brazil. The behavior is very similar, right? The behavior is very similar in a way that at first the number of cases were increasing very rapidly, but at some point that speed began to decay. And I mean, even though the number of cases continue to grow, it is not doing it as fast as before, right? Okay, so all these curves have kind of the same behavior, right? Kind of the same behavior. Maybe the green curve for the US has a kind of an erratic behavior if you compare it to the rest, but it's more or less the same. Okay, so we're going to talk about a model, a mathematician model that tries to explain or predict what happens with this kind of curves. So this function right here is called a logistic function, and its graph is called a logistic curve. Okay, this is a logistic curve. Okay, this is the graph of a function of this type here. Okay, from GeoGebra, I picked some values for the constants a, b, and k, which are all positive constants, okay? And let's see how those constants, or let's see what the value of those constants make to the graph, okay? Let me share with you this function right here, okay? Here we have the function I talked to you about, right? This is the logistic function. And now let's see what happens when b changes, okay? As you can see, when b changes, well, simply the function, the green curve goes up, right? The bigger b is, the taller or the higher the function gets, right? If you look closely, actually the value of b is an upper bound for the green function, for the logistic function, okay? So if b is 4, then it means that the curve at the long term is going to get closer and closer to that value, okay? Of course, it's never going to be greater than that, right? So that's what happens when b changes, okay? What happens when, okay, I'm gonna set it to b equals 4. What happens when a changes? As you can see, as a changes, what changes in the curve is the value of the function evaluated in 0, right? That's what happens when we change the value of a. What changes is f evaluated in 0. Okay, so the initial value, let's call it like that, the initial value of f depends on the value of a, and when k changes, when k changes, what changes is how fast is the function increasing at first. Okay, so that's what a, b, and k do to this function, right? Okay, let's take a look at this stationary curve here. So for b, for the value of 3,5 for b, we have that the curve is never bigger than that, right? That is an upper bound for that function. When a equals 5, well, f of 0 becomes this value here, that is approximately 0,6. And when k equals 0,4, well, the curve increases like this, right? Okay. So, as I was saying, this curve is very similar to the curves that we were seeing for the coronavirus, a number of cases of coronavirus. It turns out that this function helps us model the spreading of diseases. Okay, let's take a look at this here. It models pandemics, right? It models population growth. Okay, actually, this function was found out by a French scientist who was trying to model population growth. It also models rumor propagation, right? Fake news. I'm sure you've heard all about that, right? It also models how rumors and fake news grow. Okay, and these are the observations that we were making before, right? F of 0 depends on b and a, like this. That's not hard to see. We just have to evaluate f in 0. Then we
Hey,
will get
Gerardo, sorry to interrupt you. It seems like Alexi had her hand raised. I think she has a question. Alexi, do you have any question?
yes, please. Questions.
Oh no, I probably did that on accident. My bad, you guys.
That's okay. Okay, continue, Gerardo. Sorry about that.
Okay, no problem. So, as I was saying, f of 0, we can see that here, when x is 0, then the exponential becomes 1. and we would have b over 1 plus a, right? And as I was saying, the limit of f at infinity would be b, right? Because this exponential here is actually a denominator. It becomes 0 when x is, or when x goes to infinity, right? So we only get b over 1, which is b. Okay? Okay, so we're going to talk about the derivative of a function and what it tells us about f, right? Well, you have seen how to derivate this kind of function, right? We can rewrite it as b times this parenthesis to the power of -1, right? So in order to derivate it, we just have to put this negative down here. It turns into a -2, and multiply it times the derivative of the parenthesis, right? Which is basically an exponential function, right? So the derivative of 1 is 0. The derivative of the exponential would be the same exponential times the derivative of the exponent, which is negative pk, right? So there it is. That's the derivative of f, and we can rewrite it like this, okay? Now, what we have here is the graph of f and the graph of its derivative, right? The green curve, you already saw it, right? As I was saying, b is an upper bound for that curve. It's called the carrying capacity, right? When we're talking about population, there's always constraints, right? Maybe lack of nutrients or lack of space that make the population I'm sorry, that make the population not grow infinitely, of course. When we're talking about the propagation of a virus, of course, it will only affect susceptible people, right? Maybe people that are unvaccinated, etc., right? Well, as I was saying, the red function that we have here is its derivative, and it has an extreme point, right? It has an extreme point that happens when x equals 1, 15 approximately, right? Okay, so when x equals 1, 15, f prime has an extreme point, okay? And what's the effect of that point for f, right? What happens here? What happens when we evaluate f in that point where f prime is extreme? Well, let's see what happens, right? That's the question that I make here, right? When does f prime reach its maximum? Where does that 1, 15 come from? And what's the value of f at that time? So in order to get that 1, 15, in order to know where f prime reaches its maximum, we have to derivate it, right? So when we derivate f prime, we get the second derivative of f. It's a kind of a long process, so I just wrote it here. This is the second derivative of f. And in order for that to be 0, this parenthesis here has to be 0, okay? Because a, b, and k are positive constants, and the exponential never gets to be 0, right? So the parenthesis has to be 0, and from that we get x, right? It turns out that the derivative of f will be 0 when x equals the natural log of a over bk. So for these values of a, b, and k, that happens to be 1, 15, right? And when we evaluate f at that point, we get a simple number, right? A simple value for f. It's b over 2. So this is the graph. This is the graph. So we know that b is an upper bound. It turns out that this extreme for f prime happens when exactly when the function gets to be b over 2. Okay, that's the halfway to get to the carrying capacity. Feel free to ask any questions while I'm explaining all of this. Okay, we're going to end this presentation with an easy example. Okay, it says here public health records indicate that 2 weeks after the outbreak of a certain form of influenza, approximately Q,000 people had caught the disease. How many people had the disease when it broke out? How many had it 2 weeks later? At what time does the rate of infection begin to decline? And if the trend continues, approximately how many people will eventually contract the disease? Okay, so first of all, how many people had the disease when it broke out? Then we just have to evaluate Q in t equals 0. We already saw it was b over 1 plus a. If you don't remember that, never mind. You're just evaluating the function here. E to the 0 equals 1. So we get 20 over 1 plus 19, which is 1, right? This means that 1,000 people were sick when the disease broke out, right? And then how many had it 2 weeks later? Then we just have to evaluate Q in t equals 2, and then we get this here, right? This means that 7,343 people are going to be sick in 2 weeks from now, right? Or 2 weeks after it broke out. Then, at what time does the rate of infection begin to decline? That means when the derivative of Q, in this case, reaches its maximum, right? Because that's when it begins to decline. Okay, so we already know the answer to that is the natural log of A over BK. In this case, it would be 2.454, right? So that means that after 2.5 weeks, more or less, after 2.5 weeks, the rate of change of this function here begins to decline, right? So the disease slows down. Okay. It also means that the number of people infected gets to be half of what is going to be, right? Eventually. And finally, if trend continues, how many people will eventually contract the disease? Well, that's B, right? That's the limit of Q at infinity. And we all know that, or we already saw it, it was just B, right? The number that comes up here. So the answer would be that eventually 20,000 people are going to catch the disease. Okay? So this is what I prepared for you guys. I hope you found it interesting. Right now, we're going to go to Gabriel. Thank you very much.
Hi, thank you, Gerardo. This was really interesting. Does anyone have any question, commentary, or anything? George or Allison?
No, I just
No, I was just going to say it's been very fascinating, interesting, and kind of a revisit of some of my old classes. So appreciate the excellent information.
Perfect. So, sorry, people screaming here. So, we just wanted to like basically announce the raffle, and then Eduardo Rojas from Loomis Engineering is going to like introduce the externship program with Papaya. So, Eduardo, are you here?
Yes, I am.
Okay. Well, we can wait 1 second for Sandra. I'm just going to show something. Hold on.
Sure.
Okay. Hold on. Okay. Sorry, it's a lot here. So yeah, so we were looking at all the people that were in the chat, and basically, we're going to draw one person that won the raffle today. We'll reach out to you by email. So we'll announce it now. So Melissa from Melissa from FIU, you're going to win the raffle today. We're going to reach out to you. Thank you for tuning in. We saw that you commented before and you reached out to us today. So thank you for joining. We're excited to send you all your gift. And thank you for sticking to the end. So basically, Eduardo, do you want to kind of like introduce what's the externship, what is going on there, and what are you looking for? And please tell us more about Loomis Automation.
Yeah, sure. Thank you for having me. I want to thank Sandra and Papaya team for putting all this together, and George. It feels amazing being a part of this team. So really quickly, just a quick introduction. My name is Eduardo. I am a mechanical engineer from Chico State. I graduated in 2014, and I am the founder of Loomis Automation, one of the founders. My other partner couldn't be here today. His name is Brett. And I'm also the founder of Engineering Memes Guy, which is a meme page on Instagram. For those who don't know about it, go look for us, Loomis Automation and at Engineering Memes Guy. So yeah, today I'm excited to announce the externship program that we're doing here in Orange, California. For those who don't know what an externship is, it's it's like an internship but shorter in time. And what we're trying to do here is just give people practical experience where they can at least add some experience in their resume. So right now we've had, I want to say about 10 interns this year, and they've all gone to different companies like Northrop Grumman, Raytheon, stuff like companies like that. So we're pretty happy that they've gotten dream jobs for them. So a little bit about Loomis too. We do industrial automation. So what that entails is we get into machine design, we get into electrical controls, motion control, and software integration. As you can imagine, machines require a lot of pieces, and it's not just physical pieces, but also the software side of things and making everything work. One of these videos that they're showing here is we're filling some vials, and we pretty much created the machine from scratch, did a lot of research. So we do a lot of things like that here at Loomis, and really our goal is to drive the automation revolution. We get into many different fields right now. We get into medical field, aerospace field, even the cannabis industry is keeping us really busy, even military projects. So with what we do, we can get into pretty much all aspects of machinery and automation processes. Feel free to ask any questions if anybody has them. And for those wondering what type of talent we're looking for, mainly, well, right now we have mechatronic students that we are looking for mechatronic students that are passionate about automation. Also mechanical engineers, electrical engineers, and people that like to program. So if you guys are into programming, we also do that here.
We actually have a slide. We have a slide on information. So if you can go up on that slide, Gab. I think it's the previous slide. It's about the externships. I think it's that one. Yeah, so we added a slide to name all the majors, and then that's the one. So the reason why we really care about this externship, and I'm sorry, I was in like a work call. So the reason why we care about this externship program is because we want to, like, we care about minorities and underrepresented communities, and we know it's so important to put something on your resume. It is known that a lot of like people of color don't graduate with an internship. So an externship is a perfect opportunity for you to showcase your talents, put on your resume, and maybe even get a real job at Loomis. I know these guys are amazing. Do you? Okay. And I actually worked in the shop with Eduardo. They're very excited. And it's very cool, Eduardo. I don't know. Like I said, I was in a work call, so I don't know what I missed here. But Eduardo comes from Chico State, and his partner comes from Purdue University. So they're both very smart and very passionate, and they really care about helping our communities, our students, about empowering us. And they want to show you, hey, are you a mechanical student, but maybe you want to switch to electrical? Like, that way you can actually taste like what you're studying and see if you actually like it, or if you want to switch majors. It is important. Your happiness is important to us. We announce the real opportunity. Well, not the real opportunity, but we're going to send an official communication on January 15 about the externship programs. But for now, you can send your resume to info@lumisautomation.com. And yeah, I know that, he cares about helping. We're all here for each other, and we just want to make sure that, we do anything we can to help our students. So yeah, I don't know if you want to say anything else, Eduardo.
I do. You brought up a point about people changing majors, right? And that actually has happened here, where somebody thought he wanted to do like a mechanical, and because of everything that we're doing, he actually changes major to mechatronic. So people are definitely making life decisions here, like changing their life, and they're choosing, path based on what they're seeing here. So it's pretty cool to be able to influence people that way, and it's, if they like it, then it's easy for them to stick around and help out. And right now we're not doing paid internships right now, but we do give people time to gain experience and then become valuable. We have like a 3-month program as well, where after that time we can start paying people.
Yeah, exciting. And he actually looks like he just graduated college. So I think it's pretty cool that, like, they took that leap of faith and they opened their own company. And we like really young entrepreneurs here. So yeah, that's pretty cool. Okay, well, I would like to let you go to bed or go watch your favorite Netflix show. Thank you so much for attending. Gabrielle, Eduardo, I would really like you guys to say thank you too, because you put so much work on this. So I mean, this Gabrielle and Eduardo have worked so hard on this. So thank you to you guys, and I really hope that this calculus workshop can help you, go make the best out of your calculus finals. If you have any tutor needs, or like if you have any questions, don't hesitate to message us through Instagram. You can request a tutor. We'll give you free codes, so you can also get prepared with one-on-one tutoring lessons. I know that I'm working with other chapters to make more workshops for you guys, so don't hesitate to reach out. We're here to help, and I'm very excited to be part of your college journey. Thank you.
Thank you, Sandra. Thank you, all of you guys. It was wonderful.
Thank you.
Thank you, George. Thank you, George and Allison.
Yeah, George, you're the best. Thank you. And thank you to our tutors too. Thank you.
Have a good night, guys.
Have a good night. Thank you.
Thank you, everybody.
Thank you. Bye, guys.
Bye.